All right, so these are the formulas for the Fourier series. Now, some textbooks have a slightly different formula. They would actually have, instead of putting a 2 here, they might put a 2 here. Now, why would they do that? Well, the advantage of this is that this just becomes a special case of this, because if n is 0, cosine 0 is 1, so you just get that, right? So in that case, you can just live with 2 formulas rather than 3. Depending on which textbook you use, sometimes people prefer the one that I'm doing right now and the other version. Actually, if you watch my other YouTube videos for differential equations, I use the 2 over here. Okay? But I'm trying to make both versions available. Okay. Now, I think one of the examples that we did before was the following. If you have y equals to 2 absolute value of x on negative, was it 4 to 4 or 2 to 2? Which one did I?
2 to 2.
2 to 2? All right. So if I did this here, the result of this calculation was that this is equal to pi squared plus summation n from 1 through infinity. See, this is an even function, so bn's are 0. You only get an's. And an's came out to be 4 over n squared pi squared. I hope we're right. Is it n pi or n squared pi squared? N squared pi squared, yeah. This one with negative 1 to the nth power minus 1 cosine n pi over 2x. Okay. So one thing that you see from here is that you're representing a function only using cosines. You can also think of this as cosines because, just like my comment, when you plug in 0 into the cosine function, you get the constant. So even this can be thought as a cosine function. Okay? Cosine 0x, okay? And cosine 1x, and 1 pi over 2x, and so on and so on. So this one, what you see here is called the cosine series. On the other hand, if you had y equals to 2x on negative 2 to 2, then this one I have to do it, I can't. Okay, let's see, 2x, and then I'll need the sine of it, n pi over 2x. 2 over n pi minus cosine n pi over 2x will be the integral. The other signs will disappear, so it will be negative 4 over n pi, negative 1 to the nth power, sine n pi over 2x, summation n equals to 1 through infinity equals to 2x. Should be right. Okay. Yeah. Let's just say that I did the calculation. This is what you have. Okay? So this time, because this is an odd function, you're only going to see the sine terms, right? If you have an even function, you only get the cosine functions. If it's an odd function, you only see the sine functions. Then it turns out that when we solve the heat equation, we do find the need to express any given function only using cosines or only using sines. Okay? Now, how would you do that? Well, let's say you're given a function not on a symmetric domain, but from 0 to some L. Okay, if it's given from 0 to L, then there's a way to represent f of x as sum of cosine functions like this one, or just sum of sine functions like this one. I mean, you can choose one of the two. Of course, you can just also make a mix of them, but that's not needed. We actually, In some cases, we only want the cosine. In some cases, we only want the sine, right? Okay, so how do you choose to get only the sine, or how do you choose to only get the cosine? What would be the idea here? Yeah?
You just solve for an or you solve for bn, and you get rid of the other one.
Yeah, but then our goal is to make them equal, right? So if you just randomly delete the other one, it won't be equal anymore. Yes?
So to the sine function, you do odd extension.
You do the odd extension, right?
If you do the even.
Yeah, so what you do is, see, the function is only given on the right side, right? Now, if you extend this function, so let's call f e as the even extension of x, so that it looks like this. It's symmetric with respect to the y-axis, okay? If you take this and plug it into these formulas, then bn will be 0 because you have an even function, right? And you're only going to get the formula that looks like this. That's called the cosine, Fourier cosine series, okay? On the other hand, if you're given this, and you do the odd extension, which is like it's a point symmetry with respect to the origin. So you take any point, you draw a straight line through the origin, and you need to have the same length. And there's this one. So if you do that, then it's a bit hard for me to draw. Let's see, what would that be? I think it's like this. Okay, so it's like flip once and flip twice, and you get this. Okay. Then this function will be called the odd extension of x. This is not 0, this is a letter O. It's a poor choice of symbol there, I'm sorry. But this is the odd extension. I'll just write ODD, that's better. Okay. F odd x would be this function. And if you take the Fourier series of this, it will make the a0 and an disappear, whereas the bn will be the only survivors, and you're going to end up with the Fourier sine series. Okay? Now, lucky for us, we don't have to think about how to get these functions. I mean, for example, the odd extension will be like, I don't know, the even extension will be like f of x if x is positive, but if x is negative, we put f of negative x. Then that's the formula for getting the even extension, and if you put a minus here, that'll be the odd extension. But lucky for us, we don't have to consider this at all, because at the end of the day, this won't be used in the formula. So let's think about the following. Suppose we worked with the even extension. Then automatically bn will be 0, but let me now erase this one. But when you do the a0, which is 1 over 2L from negative L to L of f even extension of x dx, but then we can use the doubling trick, right? You integrate over the half the interval with double the integral, right? Then what you get is like, see, both even extensions or odd extensions would agree with the f of x from 0 to any L, right? So you don't have to think about the even extension anymore, it's just this. Okay? And this cancels, so now you have a nice formula for a0, and then an would be 1 over L from negative L to L, f even x dx. And again, doing the doubling trick allows you to skip having to consider the extension, but just write down the, sorry, I forgot the cosine, didn't I? So it'll be cosine n pi over Lx dx. Okay? And then once you're done with that, with these two, now you can represent the function as a0 plus summation n equals to 1 through infinity of an cosine n pi over L x. Okay? So that will be the formula for the cosine, Fourier cosine series, where we're assuming that the function is defined from 0 to L. Right? Now let's see if you can come up with the formula for the Fourier sine series. So Fourier sine A0 will be 0, AN will be 0. The only thing that matters will be now BN, right? And BN would be what? Doubling. Let's say we did the doubling trick already. So, yeah. So what do we get? We get, what's the coefficient? 2 over L. 0 to L. F of x sine n pi over L x dx, right? That will be the formula, right? And once you get this, your function will now be represented only by the sine functions. Bn sine n pi over L x, where n starts from 1 to infinity. Okay? So those will be the formulas for sine and cosine.